Okay, so we're going to take a look in this case of Sophos, their free AV. And what's nice about their free AV is that it has userland hooking, which is, the same thing that most EDRs also use. So that's something we can experiment with without having to purchase an AV or an EDR or anything like that. You could also write your own um, anti-DLL or kernel based or whatever hooks using Windows detours or Microsoft detours, which is a hooking library provided by Microsoft. Um, and that's quite nice to be working with for a variety of reasons, but you can also create your own userland hooking DLL with that injected in and then play with it like that if you wanted. But in this case, why not? We're using an actual AV. Now, in this case, in terms of like identification, we're going to just take a look at how it is. So in here, I've got just command prompt, right? I just ran command prompt, and now in Rindabug preview, which is obtainable from the Microsoft Store, I'm just going to attach to cmd.exe, right? And attach to it. And now I'm going to start dumping. Let me just zoom in a little bit. I'm going to start dumping some NTDLL syscall locations. Let's take a look at NTDLL bang. What's an exported function I'm going to work with? Let's see about, I'm going to try and pick one that might not be hooked because EDRs and EVs don't necessarily hook everything, right? I'm going to think of a function that is pretty benign and probably isn't hooked. Let's see, what's a decent syscall that's probably probably safe call? What about NT trace message? Right, NT trace message is probably safe. Let me do dot reload. Huh. Is NT trace message not a syscall in NTDLL here? X NTDLL bang. NTDLL star trace star. What do I have? Oh, there's NT trace event. Maybe that's what I was thinking of. NTDLL bang NT trace event. Okay. So this is what we expect to see. This is not hooked, obviously. It moves the syscall number 5E in hex, in this case, to the EAX register and does the syscall operation. And it moves the first parameter, which is typically in RCX, in R10, because this is the syscall ABI. The syscall number is in EAX, and the first parameter is in R10. And then it goes RDX, R8, R9, stack, blah, blah, blah. This is a unhooked NT call. Simple. If I call this, it'll go straight down into the syscall. Now compare that with one that is hooked. Now I'm going to imagine NT write virtual memory is going to be hooked. Why? Because it's a risky API call. It's one that allows one process to manipulate the virtual memory of another process. Pretty sure it takes a process handle. So yeah, if I dump that, you see it's quite different. In fact, it just has a jump to some other address, and then the rest of the code is garbage. Which means when you hit NT write virtual memory, instead of it doing a syscall like this, it's going to jump to this code, and then this code is going to do something else that may or may not syscall. If I dump this, that contains another jump to some other address, blah, blah, blah. It contains some other stuff here. Most likely it's going to be filled out when we actually hit it. To see that, I'm going to grab the address of NT write virtual memory. It's this address here. And I'm going to forcefully change the instruction pointer to that address by doing R rip equals to that address. Now, when I single step through, I'm going to be single stepping on this jump here at the top here. I single step through. We hit this second jump. I single step through here. And now, bang, we are in the HMP alert module. We can see that this is the start of a function. It's got a function prologue where it pushes registers that it's going to clobber onto the stack. It makes room on the stack for local variables. And then it does a bunch of things, calls different things, blah, 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 calls different things, multiple calls, call, and then returns. We don't see a syscall instruction here, but one of these calls will probably be a call somewhere to to a sys to the actual original syscall. Actually, I'm wondering if it's going to be this one. Let's take a look. Call dword pointer. No, wait, dword pointer that. Sorry, it dereferences that. Let me dereference that. That contains this address. Let me dump that. This is ntdll loader p dispatch user call target. Okay. What is dispatch user call target? I believe that takes a pointer in one of the registers. I forget which register, and it calls that one. Let me see. Let me dump that further. It jumps to RAX. RAX is passed to this from elsewhere. So it's going to be the value in RAX. RAX contains, as we can see before the call here, RAX contains this address here. Well, the keyword pointer in the 64-bit value in this address. So let me get the 64-bit value in that address. Let me dump that. And what does this do? Move RCX to R10, move 3A into EAX. This looks very much like the syscall prologue, but instead of syscall, it jumps to this address. Okay. What's that address? That contains this, and this contains the syscall for NT-write virtual memory. That's a syscall instruction right there. NTDLL NT-write virtual memory plus 0x8 syscall. Okay. So, we just, even without, even before actually loading up this target into a reverse engineering tool, I just found out roughly how it does, where it stores, how it calls the original syscall. So I'm going to go through this just from the start, just in case I kind of rushed through it and wasn't clear. This is the first time I actually looked at this, but it did stand out to me. I'll try and clarify why it stood out. So let's go back to NTDLL being NT-write virtual memory. So first of all, when you dump NT-write virtual memory, it's got this jump here, and then it's got this garbage code. Now, just very quickly, if I do this plus 0x8, you actually see the JNE and then the syscall. If I do 0x10, no, not 0x10, 0xa. Wait, what did I do before? 8. There we go, 12. My bad. If I look at NT-write virtual memory plus 0x12, you see the syscall. Now, why we can see the syscall here at plus 12, but without plus 12, you see garbage, is because the way the instruction architecture for Intel is that there's variable length instructions, right? You can see that this jump is like this many bytes, but the next it interprets it as just these 4 bytes and then 4 bytes and then 4 bytes. So if we're not looking at the right offset or the right alignment, you're not going to see the correct instructions. If we jump at plus 12, we land at the starting bytes 0f05, which is you see 0f05c3, and before then we have Right, it's right after here. You see the 0F05C3, right? It's all junk until the 0F05C3 here at plus 12. Anyway, without even worrying about that, going back here, when we follow the jump, right, we get to where we are now. Which, let me go back to here, right? I'm just going to look at it from the top view here. We get to here, the start of the hook, which is in HMP alert. Now, the reason why I identified, where is it? This location as being the location of where it potentially calls the syscall, which it does, right? It calls the pointer in here, which contain that dispatch user call target function with the parameter in RAX, which is in here, which points to the syscall instruction in NT-write virtual memory. The reason why that was identified is because I know that it's going to be a pointer that lives in some global variable, or it's not going to be a hard-coded address, right? Because it can't hard-code the address of NTDLL's target function pointer for these things. When it does its hooks, it's going to back up that pointer, right? Which maybe I still have that here. Maybe I don't. Either way, when it patches NTDLL, right, to do the hook with the EDR DLL, which we identified as that HMP alert one, once it's safe, it's going to perform the original syscall. That original syscall is going to be the memory that it overridden, right? That syscall instruction location. And that's going to be something dynamic that is going to save off into some static global variable somewhere as, okay, when you want to do NT-write virtual memory, that lives in this global, or it lives in that global. It's not going to be a hard-coded address, because it can't be. It's going to be different per boot, as NTDLL has ASLR applied to it per boot, right? So that's going to be, I'm looking for a global variable that it's going to dereference. That's this. These addresses, right? Call here. See this address? This is hard-coded. This is a hard-coded address. Now, when I say hard-coded, that's not entirely true. This would be a relative address that gets patched to a hard-coded address by the loader, right? That's part of the relocations for this PE file that the loader will patch up into the appropriate hard-coded address. But these addresses are going to point to code either that's imported, so like an imported function or something. Actually, not even really. This is mostly going to be code that just references functions internal to the same DLL. Right? This address is going to most likely live within HMP alert itself. If I dump it or disassemble it, you can see that it does live within HMP alert. We don't have proper symbols, which is why you got this massive offset, but it lives within HMP alert. If I do bang address, it's an address that is page execute read within the HMP alert DLL, right? And because it's not dereferencing a pointer or anything, it's just a actual hard-coded or relocated address in here. Same for this jump, same for this call, same for this jump, same for this call, this jump, this call, and this call, right? They're all like hard-coded addresses. Now, of course, the actual syscall call might be inside one of these functions, but from just scrolling through, I saw this, where it's calling the contents of a pointer, which means that this is likely a global variable. This may live within HMP alert, but the actual contents of it may not necessarily. And it doesn't, right? If I dump the address of the pointer, that's a pointer within HMP alert because it's going to live probably in one of the global data sections that contain writable memory, um, things like that. Right now, it's read only, but it probably changed it to read only after it wrote to it when it initialized hooks. If we dump the contents of that and I get that pointer that it points to, right? This does not belong to HMP alert. This belongs to NTDLL. That was the dispatch user call target function. And then by looking through this function, I see that there's a jump, right, to RAX. And I can see that looking up from the start of that function, RAX is not set to anything, which means that RAX must be set before this function is called. So it's a parameter. It does some checks, but it eventually jumps to that value that's provided to it from the callee. So I go back to here where it's called and I find where RAX is set. RAX is set up here and it's set from the contents of another global, which is interesting to me because this global would have been set then with something that isn't set at load time. Otherwise, it would just be a full address like this, which means it's set dynamically most likely, which is exactly how I'm expecting the actual syscall backup pointers that it saves off to be set. If I dump the address of that pointer, of course that's in HMP alert, but this one is actually, it's read write. It didn't make it read only, which is interesting. It's actually a writable pointer. So for this target specifically, I could actually modify this to be a pointer to whatever I want because it's read write. But I don't need to worry about that. If I dump that, that contains a pointer here. And now this would be NTDLL, right? That is unknown. Interesting. This is actually the... I see. So it's not NTDLL. It's something else that just contains the syscall stub. This might be... Is this a heap address? Is that the command for it? Or is it like -p or something? I forget. Either way, some reason it's unknown. But anyway, it contains a syscall stub, but the jump that it goes to here, this one is the contents of NTDLL. Yep, it's the one in NTDLL. And that's the last jump that goes to the syscall instruction. So by following it through, it loads from some global into RAX, loads from some global, calls it. This call ends up jumping to RAX. RAX contains the pointer value in here, which is this first line here. I could also just do upoi, not that one, this one. To dereference that instead of doing it myself. That does this, which is the syscall stub stuff that we saw before, where it backs up RCX into R10, sets a hex value indicating the syscall number into EAX, and instead of syscalling, it jumps to this location. That location contains the syscall, contains the normal test JNE stuff we saw in the other syscalls, and then it does the syscall instruction, and then it returns. That does the syscall. So through that identification, we found out that if we want to find out the original syscall location for NT-write virtual memory, well, actually we have a couple options. One, we could disassemble the hook and find out where it calls, where it eventually calls into our loader p dispatch user call target, and then dump the value of RAX. And then RAX is going to be the location where it sets up the syscall number and does the syscall. Or alternatively, in this specific case, we can just find the address of NT write virtual memory and just jump to plus 0x12, which, well, actually, the problem with that is that contains the syscall, but it doesn't contain the syscall number. The syscall number was in this location here. If I go here, this sets up the syscall number and then jumps there. So we would want to actually go to this location because that contains the syscall number. Okay. So that's only for write virtual memory. What about something else? What about NTDLL, NT open process X? Open process, surprisingly, is not hooked. I thought there was an open process X or something. NT open process X MSDN. Am I wrong? Don't have network on that one. Maybe I'm wrong. Anyway, the reason why it doesn't necessarily need to hook NT open process is because there's a callback in the kernel that will be invoked from open process operations. So we can handle this hook in kernel. It doesn't need to hook it in user. So just because it's clean here doesn't mean that the EDR doesn't intercept it. This is one of the few APIs that can properly hook and handle in kernel via the PS set process notify routine function. Let's find something else. What about, trying to think, what about create thread? It can also hook. What about set thread context? Set thread context, not, oh, is that in like a different DLL? That's in kernel 32, probably kernel base actually. Let's look at kernel base then. Kernel base being set thread context. That goes to NT set context thread. That's why. That's probably hooked. NTDL being NT set context thread. Yep, that's hooked. It jumps to a different address. Let's try going to this one. Rep now equals to that. Let's step through the jump, step through the other jump. Okay. Now in this location, is there anything different? We got the call. We got a call here. This address. What's this address? Again, dispatch user call target. And again, this must be the place we want. Yep, sets up the syscall number, jumps here, and this is going to be the syscall. Yep, the syscall. Okay. But you see that it's not called immediately. First, it calls this first line. Most likely, this first line determines whether it goes through and allows it, or whether it does not allow it and it kills the process and alerts and things like that. We can view that. The current module, right, is HMP alert. If I do lm that, I can see that's at C drive Windows System 32 HMP alert.dll. I've copied that into my host here, and I've got that here, but I'm just going to open it again. Let me go to grab me Sophos System 32 HMP alert. I want to open a fresh database of it. Now the offset I'm after, let's look at this offset. So I'm going to grab the start of this function. This is the hook function for set anti-set context thread. Grab that minus the HMP alert, which will minus the base, and we get an offset of 2D5B0. Grab that offset, go back to here, and let's go to 1800 No, 1.8. All right, hang on. What's the base address here? Base address is this. This is the base address. So I'm just going to start at the base address here, put a relative address of 2D5B0, go there, and we get to this sub. If I look at the disassembly, it's a bunch of moves, a call, and then the call to guard dispatch, I call F pointer, which is essentially going to jump to RAX. I'm going to rename this to anti set context thread underscore hook. And let's see what it does in Binary Ninja, right? It calls this function with the args. Now, this is going to contain the parameters of NT-set context thread. What is NT-set context thread? Oh, it's set thread. What did I say it was in NTDLL? Let me just dump this again. Oh, it's not that one. This one. And then it jumps here. Now, you play that. NT set context thread. Okay, it's not documented on MSDN. That's fine. Just going by basically it takes a thread handle and the context pointer. So in here, this is going to be H thread for thread handle. And this is going to be a pointer to the not content. Whoops. The pointer to the context, right? So this again is P context. And this one here is H thread. So it calls this function that takes the H thread and the context pointers. And then it calls the function that, where's this call? Right. It calls the function that actually takes so this is the original function, right? It's stored at this global variable. This global variable contains the pointer to the syscall stub for that actual call, and it passes that result to this function. But it also, before it does that, it calls this function in the first place. And this, let's see, arg 1, 2, 3, 4, and 5 contain the original parameters. So arg4, this is H thread, and this is P context. Sets them in here, which probably gets set to somewhere else. And there's a call going on here for RAX, where RAX is RAX plus 10. RAX comes from RCX. RCX comes from RBX plus 48. RBX comes from RSP plus 70. RSP plus 70 goes into RBX. What's RSP plus 70? Load some globals. Calls here, which is another dispatch one. And this function call is this one here, I think. That calls a global. No, wait, that calls a global with another global. Now I'm looking for this line here. And that does a function call with RAX, which contains this value. And this value is a global that gets set to REX2 here. And REX2 comes from RTL first entry S list. So this global is a function pointer to RTL first entry S list. If I go back, not back too far, in this function, you've got RTL first entry S list stub. So it's calling first entry S list against this, sets that to that, does some checks and stuff. There's other calls in here as well that was happening. I'm not going to bother reversing this too far. Where's RAX? Great. It's checking in a list. Oh, what's this call? This is Rax. Rax comes from plot 10. This comes from RCX. RCX is RBX plus 0x48. 0x48 goes into there as well. I'm not going to reverse that struct to find out what it is. Either way, it's enumerating a list, doing some certain things, checking things, and then going to call, and then, returns. Well, actually, you can see that based on the result of certain things, it can throw standard bad alloc, which is going to throw an exception. And that can raise an exception and crash. So, and I imagine there's an exception handler in here as well that can handle that and determine what the fault is and determine that it's probably from something bad. Where does that happen? That jumps equal to, what's this address? Okay, that's a return address, but if it doesn't jump equal to, it falls through here. It can fall through there, fall through, jump, or where does this get called? This gets called up here, right? If this equals to arg2, arg2 to this function is 0 on the first call and then 1 on the other one. So 1 is after it's already called, 0 is before it's called. So arg2 is kind of key in determining what can happen. And I see that it can fail. I wonder if that's because if we skipped over that and then did it here and it hits here, it'd be a problem. That's fine. We don't need to skip over there. But you can see how it does processing on it anyway before it goes there. That's the main point, really. So based on all this and based on what we saw, and this is going to be like the original function call, we can figure out how we're going to get around this, how to avoid this hook. And there are multiple ways. But because we're going to do it a way that at least I haven't seen publicly really done at this point in time much. So it'll be a little bit more interesting. And the fact that disassembling or being able to disassemble in your own code is quite useful for offensive purposes. Especially, I mean, I've done it more so in kernel. I mean, you want to disassemble the kernel to find pointers to global variables, the SSDT, things like that, that aren't exported. So you have to find pointers to them, and you find pointers to them by doing pattern matching via disassembling and things like that. We're going to do the same sort of thing, pattern matching with disassembling here to find the stub that handles the syscall for every hooked function. And we're going to patch our import address table. So our import address table, when we're loaded, is going to look something like this, right? We're going to have essentially an import address table, and that import address table is documented in the PE format. And that's essentially just a bunch, well, we're going to support only 64-bit processors, and it's going to be a bunch of 64-bit addresses. Just pointers, 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 pointers. And these are all pointers to other modules, to other functions. Pointer to NTDLL, NT write virtual memory. Pointer to kernel base, set thread context. Pointer to blah, 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 right? What we're going to do is, one, get the IAT. Two, disassemble the function pointer in the IAT. Three, determine if it's hooked. If it's hooked, disassemble to identify the syscall stub pointer. 5, replace the IAT entry with the syscall stub pointer. And that's it, really. There's some other things that'll have to happen. If the IAT is not writable, then we're going to have to use something like virtual protect or whatnot to make it writable so that we can overwrite the entry in the IAT with the new entry. And that's going to be the syscall stub pointer, which should work fine, right? Because if we set it to this address, right, which is the stub pointer, that means that our code is going to do a call here. We'll go here. I mean, not here, sorry. The one before here. We'll call here. We're going to call here, which is the syscall stub pointer, which is going to be different for every syscall, obviously, because the number changes. And then in here, which is why you can't hard code it. And then when it's here, it's going to set up the syscall stuff. It's going to jump to the address that does the actual syscall, and then it's going to return. And that's going to return to the original caller. And there's another benefit to this over using direct syscalls. Now, I haven't actually seen this used by EDRs before, but there are some tools that use this. And there's ways to inspect the return address of a syscall after a syscall has been completed. And using that, code and programs can determine whether a syscall was executed within NTDLL or what other module is executed in. Now, syscalls don't normally occur outside of NTDLL, unless, of course, it's like user32 or GDI+, right? There's set OS DLLs that do the syscall instruction. There's no, well, I haven't seen any legitimate, like actual legit code that will do a syscall in its own module. The syscall will typically originate from a OS system DLL like NTDLL, user32, etc. So if you're doing inline syscalls or direct syscalls like some malware does or some public code does, you can detect if it's an inline or direct syscall by using the OS components to determine whether the syscall's return address lives in a system DLL like NTDLL or lives in some other DLL like mymalware.dll or .exe, right? Now, again, I haven't personally seen EDRs do that, but it is something you can do. By doing it this way, by patching the IAT to the correct stub here instead, this eventually flows to syscall in NTDLL. So you prevent, well, you get around that direct syscall detection. Of course, we have other things we're doing that's not entirely normal, like patching our IAT after we've already loaded. But most things that you do are going to have their own individual detection points. Some more suspicious than others. But anyway, we don't need to get into comparing them so much at this point. There's outside of the other public ones, this one will be a fun one to work with. So this is what we're going to do. Now, this is the challenge, and I'll be walking through the solution next to achieve this. And, it's kind of generic. It works against Sophos here, and we'll test it out. but um, it'll work against any EDR that does something similar or in a similar format. Now, granted, EDRs and AVs may do things very differently to each other. So there's a chance that this would work here, but it wouldn't work on other ones. If you want to handle those other ones, then that's where in your kind of unhooking code, you can detect whether you successfully found the syscall stub or not. And if you didn't, but the target is still hooked, then implement some fallback. What do you want to do on a fallback? You can kind of play it safe, send out a message out to your C2 server saying you couldn't patch things, and maybe even dump out the disassembly to the C2 server so that us as operators can see that disassembly and decide what we want to do to get around that. Or you can fall back to another method like direct syscalls or patching in a clean version of NTDLL or whatever you want. But we're going to do this method for here for now. And we're going to use Rust. There's a nice disassembly framework in Rust called iced 86, iced x86, Rust. This crate is quite nice, all in Rust. It's probably one of the better ones that I've found. There's also like Capstone, which you can compile as a clib and import, which is one that I've used on kernel drivers before. But we're going to use the iced x86 in this case. You can also write your own, of course, but it's not worth doing that for this little POC. This is the crate we're going to use for disassembly. And so give that a go. You know, you're aware of the steps we want to do. Here's a crate to disassemble. We've got already some PE code from like the COF loader and that. We can extend it to handle getting the import address table, which is in the PE format, right? The PE format has an import address table, which is valid for loaded processes in memory, has descriptions of what it is. Yeah, give it a go. And then we'll go through the solution together. If you want to verify that it works, run it on your target where you have something like Sophos installed, attach a debugger to it, and step through one of the syscalls that you're doing that you know are hooked. So in this case, we know NT-set context thread is hooked. So maybe I'll write some code in my Rust code to call this. Or if you want another one, NT-write virtual memory, right? This one's hooked as well. So just call this function in your own Rust crate and run it once without doing the unhooking to confirm that you do go through the hook, and then run it again, this time doing the unhooking and see if you avoid the hook entirely and you go straight to that syscall stub, syscall and return out properly, avoiding the hook. Once you confirm that, then we'll confirm we bypass detections by creating a Rust program that uses one of these hooked APIs to do something that triggers Sophos's detection and crashes our code, and then running it again with the unhooking and verify that it doesn't get detected, and then it goes through fine. Give all that a go. Once you've had enough time playing with it, we'll move on to the solution.